Okay, folks, so this is going to be acids and bases that we're going to talk about today. And many of you are going to notice that this is something that you've probably talked about, heard about before, and you've actually experienced quite a bit of in your lives, but you've never probably thought about them in a concrete, qualitative, or even quantitative manner. And so, acids. How do we know it's an acid? Well, first off, most of the things that you've tasted that are sour have probably been acids. For example, orange juice, acetic acid, which is vinegar. Those are all citric acid, by the way, is orange juice. Those are all acids, and that's the reason those things taste sour. It will turn a litmus paper red. It'll react with active metals to release hydrogen gas. So if you were to pour acids on many different metals that would react with them, things like iron will react very slowly, but things like potassium and sodium would react very fast. They would produce hydrogen gas, react with bases to form water and a salt. So if you were to mix an acid and base together, one of the most common forms of products would be making water and a salt like table salt, NaCl. Bases are going to taste bitter, and so most of the bases that you've known and experienced in your life are going to be a bitter taste to them. They're going to turn litmus paper blue. They'll feel slippery on your skin. This is actually because bases will slowly turn your dead skin and your live skin, if you put enough of it, into soap. Okay, and this is called saponification. It's actually how you make soap. You take fats, usually animal or plant fats, and you put them with a base, which will make the soap molecules. Reacts with acids to form water and a salt. Again, acids react with bases to neutralize. And neutralization will make water and a salt for most of those cases. Here's some different examples of these. These are acids over here, like vinegar, vitamin C, citric. This right here is a bunch of different bases. So this would be, most drain openers are a base so that it can essentially react with you. Most things that clog drains are things like hairs and fats and flesh from meat that you use, etc. And so to unclog a drain, usually what you need is a pretty strong base to react with those and make soap out of them. These are also some other different types of bases. For example, baking soda is a carbonate, which is a type of base. This is ammonia, which is a type of base. That's that NH3. And again, this is another type of base that you can use as an antacid. By the way, the baking soda would make CO2 if you're curious when you mix it with acids. As some of you, I've seen some videos detailing this experiment and this reaction. And they were quite fun. You guys did a pretty good job, actually, overall. Then here's the salts that we talked about before. Many acids and bases, when they react together, are going to make salts. And so we have, for example, aluminum sulfate here. Here we have NaCl, which is table salt. And here we have Epsom salt. Okay, so the Arrhenius theory of acids and bases. It's the pretty much simplest ground floor theory. It covers a lot of different acids and bases, so it's pretty widespread and easy to use. So in the Arrhenius theory, an acid will be a molecular substance that ionizes in aqueous solution to form hydrogen ions. And so an acid will produce H+ in solution. And these are some different common acids that do so. Sulfuric acid, hydrochloric acid, etc. Okay, so the Arrhenius theory bases are going to be substances that produce hydroxide ions, which are OH- ions in aqueous solution. So if you were to add a base in the solution, it's going to make OH- in that solution. And here's some different examples of that. Here we have sodium hydroxide. This is one of the, and potassium hydroxide. By the way, together, these are what are called soda ash or potash, depending on the quantities of the two that you have. Here you have lithium hydroxide batteries. These are commonly used in lithium hydroxide. These are commonly used in like batteries and stuff. And then you have some more different ones, of course. Magnesium hydroxide, by the way, is the most common antacid that you'll get. It's like that milk of magnesia that you hear about or use. Neutralization is going to be an acid reacts with a base. The properties of each are neutralized, and the products are going to be typically a water and salt. So an acid reacts with base and will produce a water and a salt. So there's some limitations to this Arrhenius theory. The H plus ions do not actually exist in water solution as H plus. Protons will actually react with the water molecules to form hydronium ions. And so when you hear about H plus being in solution, that's not really a thing. It exists as H3O plus in solution. We just refer to it as the H plus. Kind of like when you refer to arms, you're referring to usually people with arms. All right, now the Arrhenius theory does not explain the basicity of ammonia and similar compounds. There's actually many different bases and acids that the Arrhenius theory doesn't really encapsulate. It doesn't include. But it's a decent ground floor explanation and understanding. It applies only to reactions in aqueous solutions. If you have an acid that's not in an aqueous solution, the Arrhenius theory doesn't apply to it at all. If it's not in water, if you haven't dissolved it in water, the Arrhenius theory falls apart. It doesn't really exist. It doesn't really make sense. So there's an alternative theory that was proposed, which is the Bronsted-Lowry theory. And the Bronsted-Lowry theory encompasses a much larger scope of the world and the world of acids and bases. So an acid, according to the Bronsted-Lowry theory, will be a proton donor, meaning it's going to give a proton to something else. So for example, this HCl right here is going to give its H plus to the water. That's why you get H3O plus, excuse me, and the Cl minus that's left behind. Notice again, the Bronsted-Lowry theory is actually quite straightforward on what's an acid, has to be able to give away an H plus. And so this is always the acid because it gives away the H plus there. And the products from Bronsted-Lowry theory are always very nice and easy to predict. So you always lose a positive charge, meaning you get one more negative charge than you would have been, and you lose an H. Ta-da. So the base is going to be a proton acceptor. So in the case of Bronsted-Lowry theory, the base, right here's our base, is going to accept a proton. And so we go from NH3 to NH4 plus. Notice we've accepted an H plus. Now, the Bronsted-Lowry acid then was going to be whatever donates the H plus. So notice in this case right here, water is actually our Bronsted-Lowry acid. In this case up here, the water was our Bronsted-Lowry base. And that's because it is both an acid and a base. Water acts as both an acid and a base. Okay, so this again is the overall example of a Bronsted-Lowry theory. Again, your acid is always going to donate an H plus. Your base is always going to accept an H plus. Notice that to accept an H plus, your base needs a lone pair. And so how do you tell a Bronsted-Lowry base? It's something that has a lone pair that it could accept an H plus on. Salts are ionic compounds composed of cations other than hydrogen and anions other than hydroxide. So a salt is essentially not a base. Okay, it's essentially the most basic definition of acid-base. It's not that. So again, salts, ionic compounds, they're not going to have hydrogen or hydroxide. Anhydride means without water. An meaning without, hydride meaning water. So non-metal oxides are going to be acidic anhydrides. So if you have a non-metal with a bunch of oxygens on it, and it doesn't already have H's on it, it will be an anhydride, meaning that if you put it with water, it will react with the water. Okay? Metal oxides are going to be basic anhydrides. So if you have a metal with an oxygen, it's going to be a type of base. Like, for example, we have calcium oxide here, which is lime. This would react with water to give slake lime, which is this one right here, which is your calcium hydroxide. And again, that means that it is basic because it's going to make a fairly strong base in solution and give you lots of OH minus ions in solution. A strong acid, this is going to ionize completely in water solution. So HCl is a strong acid because it comes apart completely when you put it in water. A weak acid, on the other hand, is only going to partially ionize in water solutions. So a weak acid is only going to partially come apart in water. So here we have HCN. Most of it will stay together when you have it in water. Only a little bit of it will come apart and give you H plus and Cn minus. Now, please do not get confused. Many people, when they first learn this terminology, they think of strong acid and they think of reactive. So they go, strong acids, those must be very reactive, right? And that's not necessarily true. Reactivity and strong or weak acids, those are not exactly linked, okay? So a strong acid just ionizes completely. HCl is the acid that's in your stomach. That's your stomach acid. So HCl is not super reactive. It's in your stomach right now, and it is completely dissociated, which is why it is a strong acid. Now, a weak acid such as HF is a weak acid, but HF is extremely reactive. If you've ever seen the scene from Breaking Bad, that's pretty much true. HF, if you were to put HF on a person, enough HF, you would dissolve them. If you didn't do it in the correct container, like if you tried to do it in a bathtub, it would dissolve through the bathtub. It would react through the bathtub. It would burn a hole through the floor, burn the hole through the floor below that probably, and it would probably end up as a puddle, completely reacted away, down somewhere in your basement where it reacted a portion of the soil away. And so, yes, HF is extremely reactive, but it is a weak acid because it only partially dissociates in water. Okay, so strong bases are going to ionize or dissociate completely in water solution. For example, NaOH is a strong base because it completely dissociates, comes apart as Na plus and OH minus when you put it in water. Weak bases will only partially dissociate in a water solution. So for example, or ionize in a water solution. So for example, NH3 here will only partially go to NH4 plus when you put it into water. The majority of it will actually stay as NH3. All right, so ammonia will accept a proton from water, and this will form a basic solution. Notice these uneven arrows mean that the majority stays like this and doesn't do anything, just stays dissolved in water as NH3. However, some of them will take a proton from the water, giving you NH4 plus and OH minus. And those are the ones that ionize in solution, and that is why it is a weak base. The reaction of an acid with a base will be called neutralization. Water molecules are the result of the reaction between hydrogen ions and hydroxide ions. So for example, right here we have this hydrogen ion, H+, and hydroxide ion, OH-, reacting together to form water. Notice that all water systems, all water actually is in equilibrium, meaning that you have a little bit of it that breaks apart to make H+ and OH-, a very small amount, and most of it stays together as H2O, water. So during neutralization, an acid reacts with a base, forming water and a salt. And so this is a base reacting with an acid to form salt and NaCl, which is table salt, and water. The amount of acid or base in a solution is determined by careful neutralization. This is referred to as a titration, and it is one of the easiest methods to determine how much acid or base you have in a solution. By the way, this is actually those little pool testing kits. This is how the majority of those do that. They come with essentially an acid with indicator in it. You put that in your pool, and when it turns a different color, you know what your pool pH is, okay, and what you need to do with it. This is also how you can test for what's in water. This is one of the ways they test the health of a water body, if you're curious. Okay, so right here we're performing a titration. Down here we have an acid with our indicator in it. That is this pink color that develops. As that indicator is given more basic conditions, once it reaches a basic pH or a basic conditions, it will start turning this pinkish, fuchsia, purple color, okay? And so in the immediate vicinity, before you mix them, it makes a little bit of a pink color. This right here is showing you where it's starting to turn basic in these areas, but again, if you mix that and let it set, it won't turn color. It will actually go back to clear because the majority of this is still acidic. And so eventually you make this overall solution basic, and that's what you're seeing right here. And our indicator, which is that dye that turns color, will turn that color of pink. And that's called phenolphthalein, if you're curious. So the pH scale, you've probably all seen or heard of the pH scale. pH is a means of expressing the acidity or basicity of a solution. And so the 0 to 14 pH scale that you all are familiar with is actually the pH scale for a water solution. This pH scale actually can go below 0 or above 14 as long as you're not in water. If you're in water, everything reacts with water and through water, and so the pH scale is the pH scale of water if you're in water, which is 0 to 14. So, for example, your gastric juices in your stomach would have a pH that's a little bit below 2. That would be acidic. pHs below 7 are acids. pHs above 7 are basic. And the pH of 7 is called neutral. It's neither an acid or a base. By the way, if you're curious, pure water is actually not perfectly pH 7. Pure water should be usually around the 6.9, or if it's the ocean, for example, it's actually way up here. But pure water in of itself is actually, at most temperatures, slightly acidic. Now, this is actually because of the temperature. You don't really have to worry about it too much. It's close enough to 7 that you're probably not going to ever really have this be a portion of your life, okay? Okay, so for example, soda, why it's so bad for your teeth, is your teeth are a carbonate, which is like baking soda. Soda, cola drinks in particular, are acidic. They will react with your teeth in a neutralization reaction, releasing CO2, much like a volcano would in an elementary school classroom. Tomatoes are slightly acidic. That's what gives them their particular flavoring. Urine is slightly acidic from the urea in that. Blood is slightly basic. Seawater is more basic than that. Though seawater, you've heard of the acidification of the ocean. It's becoming less basic. That's why it's called the acidification of the ocean. Most cleaners are actually basic. And here's NaOH. Now, what does the pH mean? What the pH is it's a logarithmic scale of the H plus concentration. So when you're hearing pH, what you're really hearing is it's 10 to the power, negative power, concentration of H+. So what the P stands for, it stands for negative log. And I know many of you don't have the math to really get into this. Just hopefully you know of logs and you've heard of or seen logs on your calculator and know how to essentially use those, though you don't have to get particularly into it. I just want you to understand the terminology. So pH means the negative log of the H+ concentration. This is a logarithmic scale, so when you see a single unit of pH change going from 0 to 1 or 1 to 2, that would be 10 times the concentration of H+. So when we went from pH 1 to pH 2, we went up 10 times that concentration of H+. So pH 4 to pH 1 would be, one would have 1,000 times the concentration of H+. So every unit on this pH scale is actually 1,000 times difference in that H+ concentration, as a 10 times concentration difference. So for example, when we went from 1 to 2 here, this was 10 times lower concentration of H+. When we go from cola drinks to oranges, we're talking about a 10 times decrease in the concentration of H+. So the single pH unit changes are actually huge changes. All right, these are just, again, the pHs of various different substances that we saw on that little slider. The conjugate acid-base pairs are going to be compounds or ions that differ by one proton. And so an acid, once it goes through, once it donates its proton, will be a conjugate base. A base, once it accepts a proton, is going to form a conjugate acid. So for example, when we are talking about HCl, when it lost its proton, the Cl- would have been a conjugate base. HCl would have been that acid. Buffer solutions. You've probably all heard of buffers before. They're commonly seen in makeups, shampoos, and if you go into any sort of lab setting, they're very, very common for any sort of lab setting. Buffer solutions are going to contain a pair of a weak acid and its conjugate base, or a weak base and its conjugate acid. Such solutions are going to be capable of maintaining a near constant pH. Specifically, they can resist their pH changing significantly from adding small amounts of acids or bases. Now, why would buffer solutions be important? I'll go ahead and give you an ecology example so you can have some sort of idea. So one of the reasons why acid rain doesn't have a huge effect on places like the Midwest is because most streams in the Midwest have pretty robust buffer systems. And so when you add a little bit of acid from acid rain, it doesn't change the acidity of the lake or stream and kill off all the fish. Okay? However, there are places in the world that have very, very pure bodies of water. And like the Shield Lakes in Canada. And so the Shield Lakes in Canada, they used to be very beautiful. They were very, very pure water. They had essentially no buffer solution in their water. And so acid rain has actually made those very acidic, so acidic that most of them can't even maintain life in them anymore. There's been a little bit of remediation right now, as of now, but still they at one point could not contain any life in them at all. And this is why you get bodies of water near factories that are too acidic or basic for life to exist in them. It kills all the fish. They are not strong enough buffer systems. When you get down to places like swamps, they're very robust buffer systems, and so that very rarely happens. Okay, so what is an acid rain? Well, non-metal oxides present in the air can react with water. This can form acidic solutions. Rain with a pH of less than 5.6 is considered to be acid rain. Some of the things that can cause rain to be more acidic is carbon dioxide. Not really. Carbon dioxide isn't a major factor when you're talking about acid rain. Frankly speaking, carbon dioxide is not going to cause you to have rain that's acidic enough to really cause this in a typical environment. You'd have to have something that's massively more carbon dioxide than Earth is or is likely to ever get to. Sulfur dioxide, this is the big one. Nitrogen monoxide, that's also a pretty big one. And nitrogen dioxide, that's also a fairly major one. Sulfur dioxide is usually the cause of most acid rains. And this is why, for example, acid rain is very common in China or Russia, and is less common nowadays in the United States, though it was at one point very common. So those are the major non-metallic oxides that are responsible for acid rain formation. Hyperacidity occurs when a stomach secretes too much acid. To fix this condition, you can use a base to neutralize part of that acid. And so antacids are often taken to neutralize that excessive acid and reduce the symptoms of hyperacidity. Excessive uses of antacids can actually lead to the opposite condition, and that's to an increase in the pH of blood, which is a condition called alkalosis, which is also not good for you. This is some different antacids. They all share essentially the same thing in common. There's some form of a base, usually with a few different binding agents so that they stay together, and different things to either relieve pain or make them taste better. That's usually about what it is. They may also have some stuff that absorbs gases in it to try to, make you not gassy, but you get the idea. An interesting side note is if you are willing to put up with the horrific taste, you could use sodium bicarbonate as an antacid in an emergency, and that would be your baking soda. But I would not recommend it. It's very, very unpleasant. Anyways, Tums is calcium carbonate. By the way, any of the carbonates will cause you to burp more, which is why if you ingest Tums when you have a sore stomach, you'll notice you'll start burping more because you're going to be giving off CO2 gas when you neutralize the acid. Right here are some different bases that are used as antacids that have hydroxides in them. They will come apart to give you hydroxide in solution, neutralizing the acid as a form of salt. Acid reducers have been displacing antacids in a way to combat hyperacidity. Instead of neutralizing the excess acid, you try to reduce the amount of acid you secrete in your stomach. And these are a more long-term solution. Sulfuric acid is going to be the leading chemical substance produced in the United States. It is used to manufacture fertilizers and industrial chemicals, and it is the acid of automotive batteries. If you look at many automotive batteries that are not lithium batteries, this is the typical automotive battery. Production is 40 billion kilograms per year. An interesting side note is the way that they measure the wealth of nations. Part of it is measuring how much sulfuric acid and nitric acid they make. So hydrochloric acid, HCl, has a number of uses. It is used as a rust remover. It removes lime from mortar and household plumbing fixtures. It can be purchased from hardware stores as muriatic acid. That's a fairly high percentage HCl, somewhere around 70%. This has an annual U.S. production of 4 billion kilograms. A little side note from here is that if you ever need to remove metal corrosions, you can always use acids. If you need to remove it something on an industrial scale, HCl works nicely. If you need to remove it from a car, I would actually recommend something like Coca-Cola, okay? But you can use more industrial acid. Just be careful you don't get it too high concentration, or else it will just dissolve the metal. It'll react to the metal itself. If you need to ever do something where it has corrosion on a piece of jewelry or watch or something you don't want to destroy, or have something really sticky that you can't clean up very easily. Lime juice, lemon juice, or acetic acid, which is vinegar, all work very nicely. And that can also work to remove carbonates, which is the majority of the stuff that develops in household plumbings. So those all work very nicely. You have to soak them for a bit. They'll react slowly, but they're all acids, and they're weak acids. They won't react too fast. Lime, calcium oxide, is actually produced by taking limestone, which is calcium carbonate, heating it. Under enough heat, it's actually going to cause the calcium carbonate to develop CO2 and release that into the atmosphere, leaving behind calcium oxide, which is lime. Lime can then be slaked by reacting with water to make calcium hydroxide, as we actually showed you before. Slaked lime is actually used to make mortar and cement, and it's to sweeten soil, essentially to remove acids from soil that may build up in them and thus cause the plants to die. The annual U.S. production is 22 billion kilograms a year. By the way, if you ever have soil that is causing your plants to die, this many times happens down here because there's a lot of like pine trees and stuff. The sap and needles from pine trees can cause the soil to be acidified. If you take a little bit of slaked lime and mix that in there, that can actually help a lot. So, I don't know if you ever have problems. Anyways, this is sweetening soil by adding slaked lime right here. There you go. Sodium hydroxide, also known as lye, can be purchased for home as used as oven cleaner and drain cleaner. And how it works is it literally takes, like say the oven. So in the oven you have grease that's gotten everywhere. You put the sodium hydroxide in the grease and it will literally make the grease into soap. Now keep in mind that if you let this get on your skin, it can make your skin into soap. And so I like to joke, the deepest clean you can ever get is by putting some sodium hydroxide on your hands, and you'll make your hands partially into soap. Please be careful if you ever do use sodium hydroxide. It's not actually a joking matter. It will turn parts of you into soap, and it can be very, very dangerous. It can cause caustic burns. It's actually quite dangerous. Also, if you ever work at a restaurant, please be careful. This is a pretty common mistake people make. They put sodium hydroxide in. They think it's sugar because it looks a little bit like sugar. They're not paying attention. And if you do that and feed it to somebody, it will destroy their esophagus and likely kill them. So please be careful if you ever work in an environment where you have sodium hydroxide in large quantities. Annual U.S. production is 9 billion kilograms per year. Ammonia, this is another base. This is commonly used and produced for use as fertilizer. It's also used in household cleaning products. If you've ever used Windex, that stinging sense in your nose, that's actually due to the ammonia. By the way, the same thing happens if you ever go by like a pig farm or a chicken coop. They both have a lot of ammonia that gets released from their fecal matter. And so that's also ammonia, that's that same stinging sense in your nose. The annual U.S. production is about 11 billion kilograms a year, if you're curious. Concentrated acids and bases are very corrosive to tissue and are significant health hazards. They can denature proteins in living cells. They can react the cell membranes, thus causing the proteins to burst and their cells to burst. The human body has wonderful mechanisms for maintaining proper pH of tissue, blood, and bodily fluids. That's why it's not exactly that easy to kill someone from acids or bases, but you still should be careful because it can leave horrific scars and significant damage. Our bodies are actually giant buffer systems. Remember we talked about a weak acid mixed with its conjugate base is a buffer system? Well, we transport the CO2 that we make from breathing in the oxygen and using up the nutrients to produce energy. I'm being very vague here because we haven't studied any of that stuff. But we actually transport that CO2 through our blood as a weak acid. And much of that is in the form of its conjugate base. So our blood actually has a large amount of a buffer system. So we're pretty resistant to pH changes overall. Have a great day. Let me know if you have any questions. Again, you guys can ask me just random questions. This class is supposed to be kind of fun exploration of the world around you and why things are happening around you due to science. You have access to somebody here, me, that knows a lot of those questions that you may not know or kind of, wondered about. What's the best acid to get rid of a dead body? Well, I know actually. I've actually ran a little experiment and still running experiments to determine that and determine the products that are made from using various acids and bases to try to destroy evidence in bodies. I'm partially a forensics, but I'm a forensics, spectroscopist, geosciences, and chemistry. That's what I do. So you guys have a wonderful day. Take care. Please ask me questions, honestly. It's kind of fun sometimes when you guys ask me something I don't think about.